Hello and welcome to this video where we will be continuing our journey into quantum computing. What we have seen so far is quantum linear algebra, then we also delved into the basics of quantum mechanics, and we will now go further utilizing the knowledge from those two topics to build on what we call as a quantum gate logic. To build the quantum gate logic, one of the most important notation that you have to understand is called the Dirac notation, and we will see what it is. Now, let's take a step back and think of the coin flipping game that we have discussed in the previous sessions in quantum mechanics. And what we have known is that that particular coin flipping game can be represented as a quantum state, as you can see here in terms of vector x, having an amplitude and a base states of x1 and x2 and an amplitude of 1.5. What we need to understand is that the amplitude square of the base states have to be added and remain uh, remain to a sum of 1. So now if you add 1.5 square plus 1.5 square, you will get 1, which means that we can extend it further, and the base states of x1 and x2 can be represented as a discrete base states in a vector form. And it doesn't matter if you choose 1 0 or 0 1 to represent whichever base state. You only have to be consistent that, for example, if 1 0 represents what you call as head, then the 0 1 has to represent tail. That's the only limitation that you may have. Therefore, if we now formalize this vector representation into an actual coin flipping game, we could say, in terms of the quantum state, that coin is a combination of a head state, a coin flipping game is a combination of head state and the tail state. And what we see here is a very unusually looking symbol where, for example, you see the word head and tail are in a space which is started with a vertical bar and ending with a angular symbol of greater than, and this is what basically the Dirac notation represent, which for which we will now get into more details. So how to basically unpack this? Now, in the Dirac notation, you will hear two words very commonly, and that is bra and ket. So first, let's look at ket. The point you have to derive from this that bra and ket forms what you call as a bracket. That's why it's called bra and ket. So let's look at the ket symbol first. Now, a flip of a coin can be represented as a wave function, and we do not care what kind of a wave function it is, as long as it can be represented in a combination of what you call as a basis state, head and tail, supported by what you call as an amplitude or coefficient, which is here represented by alpha and beta. Now, since we know that the quantum states are L2 normalized, which means if we now unpack this wave function and write the probability distribution, then you know that you have to normalize this by having the amplitude square multiplied by sum of the amplitude square, which means you will get alpha square divided by 1 by 2, alpha square divided by 1 by 2, and it has to add to 1. The probability distribution has to add it to 1. And you may have various possible wave functions. For example, the first one that you see has has the combination of amplitude 1 by 2 root 2, But the second one that you see has a phase shift in it. Though there is no relative phase shift because both are minus. But if you extend this further, you can also have the wave function written in the complex number format as is represented in the third one, which is I by root 2 with a phase shift represented by minus in the later component of this function. So as we said before, there can be various possible combination of the wave function. We do not care much about it as long as it follows the principle that the amplitude square should add up to 1 and the base states are representing the quantum state. The thing that you also have to remember is that the base states have to be orthogonal. That is something we will also see in a couple of slides later. So what we have gathered up until now, that the states are represented by ket, head and tail. A ket is a vector representation. For example, head can be called 1, 0, and tail can be called as a vector representation of 0 and 1. Said before, they have to the coefficient amplitude coefficient square of amplitude has to add up to 1, and the base state have to be orthogonal, which means if you take the product, or what we have learned in the linear algebra as the dot product of the two base state, it has to give you an end result of 0. Now, we have looked at ket, which is as a vector notation representing as a column. We now look at the bra functionality, and which actually represents row. In terms of what it means the complex conjugate of an vector. So bra is practically a row, a ket is a column, and the bra is represented as you can see here, where the angular sign is now becoming less than instead of in ket what we see usually as greater than. So the shape of the bracket has reversed in bra compared to what is in ket. When you now look how you should combine the bra and ket, this is the ket representation of what you see, and the bracket representation is nothing more than doing the product with the angular brackets on the outside and one bar in between, which is nothing more than the amplitude square of the coefficients. And this is how this can also be proven mathematically if you just apply the linear algebra, and you will see that this will be the outcome. So important to remember that in the way of writing this is not giving the dot product as a dot, that it is not multiplied like head and tail and represented the way we are seeing now, starting with a vertical bar, then the angular notation. The correct notation is to write it in between the angular notation with a single bar, and the bra is represented first as row, and the ket, which is we already established is a vector notification, represented as column. Now the dot product, as we said, has to be 0. You do the basic linear algebra here, and you will get the result as 0. So therefore, to summarize, the coin flip can be represented as in the quantum base states. Head can be called 1, 0, tail can be called as 0, 1, and it can have this own amplitude coefficients of alpha and beta. And this is not the only representation which is possible. You can have other sets of basis sets possible, as long as you know the two the basic principle that you have to follow. The first, that the amplitude squares should add up to 1, and the product between the basis state is 0. So for example, in you will see that there is another base state that we have chosen 1 1 and 1 minus 1 with the amplitude square. You do the mathematics on it and you will end up finding both the principle that I stated is matching. So I'll stop here. Thank you very much for watching, and I'll hope to see you in the next video.